this set was only 2. So you could have only two possibilities here, either A or either B. But if you generalize it, then it becomes cardinality of this set P. These many possibilities are possible here as for the first time step. That means these many percept sequences are possible in time step number 1. All of these percept sequences must be listed here in the lookup table. Similarly, for the second time step, you may have P possibilities here and P possibilities here. As for the this specific example, you could have two options here, 2 into 2, 4 possibilities were there for the time step number 2. But if in general you have only you have uh, cardinality of P in journal, then cardinality of P multiplied by cardinality of P. This is the number of percept sequences that are possible for time step number 2, and all of these percept sequences must be listed here in the lookup table. Similarly, for the third time step, you have, and it's a very simple, I hope you must be able to recall the counting exercises of counting problems that you had in the course of discrete structures. Okay, so this is for the time step number 3, and so on. Let's say the time span or lifetime of our agent is, let's say, T, right? Then you must have this number for the time step T. As you could see, this is P square P cube, then it becomes cardinality of P raised to the power T, so many percept sequences for the final time step T. You must add all of these percept sequences to find out the total size of the lookup table. And if you generalize, in fact, if you write this summation in condensed form, then it is summation cardinality of P, and I am using this index variable I, and I should run from 1 to T. So this is the table size in terms of number of entries. Okay. Okay, so I have reproduced this result here, that you must have these many entries, right? Okay. Um, if you calculate the table size for the lookup table for playing chess, then it comes to be at least these many entries, 10 raised to the power 150 entries in the lookup table. And for the sake of comparison, the book has given the number of atoms observable in the universe, in the observable universe, in fact, that is less than 10 raised to the power 80. So you could compare these two numbers. So that is indicative of how uh, prohibitive in terms of calculations, in terms of table size, this approach becomes. So that is quite possible. And if even if you have the storage available to store such a huge table, how would you find time to populate such a huge table? Okay, that becomes really an issue. So we can replace these huge tables by small programs. Do you have any example? I hope you must have solved some numerical uh, uh, problems in the calculus, for example, to calculate the square root or to solve an equation using some popular methods. And I expect that you must have gone through the calculation of square root uh, once we used to have very huge tables to calculate the square roots of numbers. But these days, if you I hope if you have done it already in the calculus, then that is a very simple algorithm given by Newton, and that basically starts with an educated guess of the square root of that number that you are going to calculate, and after having some certain kind of certain number of iterations, it gives you a very a result that is close to very accurate answer. Okay. If you want the answer to be precise in terms of number of certain number of decimal digits, then you have to repeat it uh, for a certain number of times. uh, that means the number of iterations, just the number of iterations increases, but that is a very small program. Okay, so that gives you an idea that we could replace these huge tables by small programs, and that is the idea behind the agents that we are going to discuss right now. That means program based agents, the agents that uh, do not use tables, that use programs instead of these huge tables, small programs instead of these huge tables. Okay, so the first one is the simple reflex agent. And if you can notice that this terminology reflex, that basically comes from the reflex action of humans, and experts believe that the humans, when they have reflex action, they simply don't think, they just take an action. Okay, blink of an eye, or uh, in fact removing your hand uh, from something very cold or very hot. So that is that reflex action, they believe that does not involve any kind of thinking. So we will see how do we how what is the reason that we call it simple reflex agent. It is the simplest kind. Okay, that's good news. And the action of the agent is based only on the current percept. That means not on the history of the percepts. Okay, so that is the reason for it being simple, right? Its simplicity basically stems from this fact that this action of the agent is based only on the current percept, only on the current input. Okay. Okay, so this is the block diagram of a simple reflex agent. As you could see that whatever it perceives through sensors, that basically is used to have an idea of the environment. This block, what the world is like now. As a matter of convention, the book uses this convention that it uses these square blocks to in square rectangles, in fact, sorry, I'm sorry, rectangular boxes to indicate the to indicate the decision process or deliberation by the agent. Okay. Okay, so whenever you see these rectangular blocks inside an agent, you must take them as decision making activity by the agent. Okay, so the agent is busy here in deciding about the current state of the environment. Okay, in this box, agent is currently busy in deciphering the current state of the environment, and once it has decided what is the current state of the environment, that state is used to look up these production rules. Now these condition action rules are the same as you have studied in the course of discrete structures, where we used to have implications. I hope you remember the implication, the basic form of implication, that we have an antecedent and then a consequent. So if this condition occurs, then this action should be taken. If this condition occurs, then the agent should take this particular action. So once the agent has decided the current state, it then uses that state to uh, see these production rules, or we call them as condition action rules, to find out a suitable rule for that particular state. And once you find out a particular rule in this particular uh, box, you the block, this particular block, in fact, again I give you another piece of information regarding the convention of the book, that these oval shaped blocks, these are the knowledge bases of the agent that you prepare in advance for the agent. Okay, so you have prepared this condition action set of condition action rules, or what we call production rules. And once this agent has decided, after passing through this block, that what is the current state of the environment, it looks into these production rules. And these production rules give some in fact it gives an action, so corresponding action that should be performed on the environment. So here in this particular box, the agent is busy, what action I should do now.